Hello, I am Guillaume Gronoff from NASA Langley Research Center and SSI. I am presenting the work Model Data Comparison of Stratospheric Intrusion over Hampton, Virginia, that was done with my collaborator Tim Berkoff, Emma Noland, Lee Charolais, and Bill Carrion. First, let's see what happened on 14th of February 2019 in Hampton, Virginia. On this Google Earth map, you can see Hampton, Virginia. The vertical curtain represents the ozone observation done by the NASA LMOL instrument. LMOL, the Langley Mobile Ozone Lidar, is an instrument dedicated to the observation of tropospheric ozone. It belongs to the Tropospheric Ozone Lidar Network, TOLNet, a set of lidars dedicated to the study of ozone in the troposphere that participated in several campaigns for studying air quality. These networks aim at supporting the calibration and validation of satellites such as TROPOME and TEMPO. The network allowed the strict definition of the input parameters for ozone retrieval, of the algorithm to compute the vertical resolution and uncertainty, and it has a standardized output for the comparison of the different measurements. Technically, LMOL is a dial lidar working in the UV. A LiCAF crystal pumps two wavelengths in the UV at about 289 and 292 nanometer. These wavelengths are tunable. This allows the instrument to retrieve ozone with 20 meter to 1 kilometer vertical resolution between 100 meter altitude and 6 or 7 kilometer altitude during the day, and a little bit more than 10 kilometer altitude during the night. The big advantage of LMOL is that it is eye safe out of the trailer, which simplifies the operation, and it is the smallest TOLNet LiDAR, which allows it to be very mobile. It can also be shipped internationally. So, since LMOL is able to observe up to 10 km altitude, let's see what happened on 14th of February 2019. Around midnight UTC, a high concentration of ozone appeared at the top of our curtain, staying for an hour, and afterwards a layer stayed around 4 to 5 km altitude. This can be better seen on the wool curtain here. This is the typical signature of a stratospheric intrusion. Stratospheric intrusions are the transport of ozone from the stratosphere to the troposphere. These intrusions are frequent in spring. They can affect local air quality as well as satellites observation, notably LIMS sounding instruments such as SAGE-3 on board the ISS. This is why it is important to address the effect of the stratospheric intrusion. For that, we can observe them and or model them. LiDARs are powerful instruments to observe SI. They can validate the timing, altitude, range, and density. However, this is only for a specified location. To be sure that we have a stratospheric intrusion and not an ozone enhancement coming, for example, from a fire plume, see Lee Charolais poster, we can use models for validating our interpretation since they are complementary. They can inform on the geographical extent of the event and they have prevision capabilities. However, models require some approximations to be useful, which lower their accuracy. Therefore, they should be validated against the observation. This is where model Lidar comparisons are useful. Thanks to LMOL, we were able to work with the NASA's GEOS-CF model. This model allows to retrieve ozone in 4 dimensions along with other species. It has been extensively used for modeling stratospheric intrusions. First, GEOS-CF was used to retrieve the meteorological conditions during the event. The cyclonic activity, like the one present that day, are favorable to stratospheric intrusion. The tropopause is wrapped around the polar jet, leading to stratospheric air being transported into the troposphere. Using the capabilities of GEOS-CF to reproduce the ozone conditions, we reproduced the LMOL ozone curtain, presented here. We see the high ozone at 8 km altitude around midnight, as well as a little bit of the ozone lingering after. That remaining tongue is less impressive than in the LMOL curtain. It is however notable that, in the model, the ozone density is less important but enhanced on a larger range of altitudes, which means that, overall, the same amount of ozone is present in the troposphere. An interesting observation is coming from the micropulse Lidar located at Langley. The MPL allowed to observe the depolarization. When we overlap the depolarization with the Lidar curtain, the ozone Lidar curtain, we see that the depolarization is perfectly around the ozone tongue. We have several hypotheses for this that we are developing in our paper. In this image, we see the good comparison between the model in solid blue and the LMOL observation in cyan. The yellow curves are the MPL observation. A more comprehensive statistical analysis of the model and the data for this event shows a very good agreement between the model and the observation. Of the 515 points of comparison, the main difference is 2.9 parts per million volume, with a standard deviation of 16.6. This is well within the 10% uncertainties of the LMOL observation. LMOL has been able to observe other events leading to stratospheric intrusions. Here, on March 28, 2019, where the troposphere has several events leading to density above 70 parts per million volume in the troposphere. We have another event here on October 17, which really looks like the event on February 14th. The rest of the ozone from this event are lingering onto October 18, which also sees its small intrusion. Unfortunately, the pandemic of 2020 prevented us from doing more observations. Sadly, this would have allowed us to test the new alert system based on the WRF-CUM and GEOS-CF provided by Matthew Johnson and Emma Noland. Let's hope 2021 will let us perform these observations. We also have a Stage 3 validation project based on the stratospheric intrusion. Since stratospheric intrusions are localized perturbations, the symmetry used in the onion peeling techniques are broken. Using models like GEOS-CF should be able to help retrieve a more accurate state of the atmosphere from the Stage 3 observation. To conclude, we are able to observe stratospheric intrusion using LMOL and have found interesting connection with MPL observation. The comparison with the GEOS-CF model is excellent, which tends to indicate that we could use the same model along with the Stage 3 to correct the Stage 3 instrument output during a stratospheric intrusion. We are submitting a paper to atmospheric environment on the subject. Thank you for your attention.